Example 2.4. Two 50-gram ice cubes are dropped into 200 grams of water in a thermally insulated container. The water is initially at 25 degrees C, and the ice comes directly from a freezer at negative 15 degrees C. A, physically explain if only part of the ice melts or all the ice melts. Now draw a T versus Q diagram with its energy bar diagram for the situation. B, what is the final temperature of the water? If only part of the ice melts, how much of it is left? This example is special because we can immediately tell that only partial melting occurs. So by looking at the quantities of ice versus water, only partial melting occurs. And then we could ask the question, how do you know this? Well, let's look at what we have. We have 100 grams of ice at negative 15 degrees C. And then we're comparing this to 200 grams of water at 25 degrees C. I mean, this is just above room temperature. There's not going to be enough heat transfer from the water to the ice to melt all of it. Most of the time, one cannot immediately determine if partial or full melting occur. It's almost impossible in many situations. So here, I want to show you how to make an educated guess. Okay, using a T versus Q plot along with an energy bar diagram. Textbooks have a tendency to make you use trial and error to answer this question. Don't use that technique. You can figure this out. So when you draw a T versus Q with this energy plot, what we do here is that this technique sets up conditions that exactly tell you which case it is. Exactly. Okay. And so even though we know that this is going to be partial melting, what I'm going to do here is that I'm going to do both cases so you could see. Okay, so let's look at the situation here. So right now, let's focus only on the ice. So here I go. So what I'm going to do here is that I'm going to do this. I'm going to go 1, 2, 3, and then I think I'm going to go to about right here. So here's going to be my T versus Q curve. So let's come up here. So this is going to be T in degrees Celsius. And this is going to be heat. And actually, I'm not going to put units for the heat. So what do I know here? I'm going to set this to be my Celsius degree line right here. And then this point right here, I'm going to make this minus 15 degrees C. Now note, I'm only going to focus on the ice. Later on, I will bring in the hot water, and so I know, or the warm water. So it's looking something like this here. So now let's go see what actually happens. So the first thing that happens is what? We have warm ice, excuse me, we have to warm up the ice from minus 15 degrees C to 0 degrees C. And of course, that requires energy. So let's see what actually happens here. So if I look at this thing, I'm going to say that this guy is going to look something like this. So I'm going to come up here. And at this point, I'm going to start labeling points so it makes it nice and easy. So I start off at A, and then I go to B. And so what you're seeing here is that this is the region where you're warming up the ice here. So that takes a certain amount of heat. So this is the heat, AB, to warm up the ice. So when I'm really looking at my situation over here, here's what I'm saying here. So this requires energy. And so I'm going to call this QAB, and this is to warm ice to 0 degrees C. Now, the next thing that has to happen is that I now have to start melting. So now what happens when I get here is that now you have water energy that partially starts melting ice. So that's the latent heat. And in this case here, I'm going to go and I'm going to say that this point right here is what I'm going to call C here. So then that means from B to C, this is where you get latent heat. So you get partial melting. So in this situation, what you're seeing here is that, look what I'm going to do. I'm going to drop a line all the way down to here. And what you're finding here is that this is how much heat you're putting in to actually, you know what? I don't want to go all the way down to here. I'm going to just keep it in line here. And so this is the heat from B to C. So again, this is this region that we're focusing on right here. Now, if there's enough energy, I'm going to call this point here now D. Now, if I have so if I have enough energy, so if I melt all the ice, if I melt all the ice, there is a critical energy. And this critical energy is what I'm going to call QAD. So it's not from B to C. It goes all the way from A all the way to D here. And this here is what I call, this is full melting. And it requires all of the energy to warm up the ice, to do full melting. So when you're looking at this, this energy now looks like this here. And this is the so-called AD, which I call the critical heating required to melt all of it. And so if I follow this, you can see that it comes all the way down to here. So now I'm going to keep this picture here. So I'm going to copy this guy. Okay, I'm going to copy this guy because I'm going to need this. So here I go. Now let's come back and add the water. So now what we want to do is that we want to add the warm water. So now what we find here is that we can determine by calculation if there is partial or full melting. By comparing two energies or two heatings. One is minus Q of the water to the critical point versus QAD critical. So that means that when I'm looking at this thing right here, what this is really telling us is that it brings the water to 0 degrees C. And so if I start to look at this thing, here's what I find. Is that if minus Q of the water is less than QAD, now remember, these are the critical values, this means that there's not enough energy to melt all the ice. So that immediately tells you that you have partial melting. But I got to calculate that number. And then the reverse is true. If I have minus Q of the water is greater than AD, then there's enough energy to melt all the ice. So in this case, you get full melting. So we need to know which situation it is. So picture-wise, here's what we really are looking at. So if I have partial melting, it's all about the bar diagram. So if I have partial melting, you could imagine that this here is the heat required to melt all of the ice. And then when I compare that to the heat of the water, well, this heat of the water is smaller. So this guy is minus Q of the water. So when I compare these two, you could see that they're not the same height. So in this case, you clearly see here is that Q of the water is smaller than QAD. So now here's the key thing here. So now if I look at I'm going to define this quantity delta Q. So this is minus the Q of the water minus QAD. This quantity turns out to be negative. So because this is negative, so what we're seeing here is that delta Q is negative. That immediately implies partial melting. Okay? That immediately implies partial melting. Now, if I have full melting, then the opposite occurs. And what I mean by that is that the heat of the water is larger than QAD. So when I compare these two, what you're seeing here is that this delta Q, which is again Q water, remember that's a positive number, minus QAD, this quantity is now positive. So delta Q is positive. That indicates that you have full melting. So we have to numerically calculate this to actually see that. So now what I want to do here is that I want to add the warm water to the T versus Q plot. And I'm going to do two of them. So here we go. So the first thing I'm going to do is that I have this one here. So what I'm going to do actually is that I'm going to take this out. I'm going to raise this up again. So now let's go see what actually happens here. So what I want to do here is that I want you to see what is the critical value. So the critical value is this guy right here, right? That point right there is the critical value. So if I look at this line, the water has to decrease in energy here, internal energy. So this line right here is my minus critical of water. That's the critical point. So I'm going to copy this 2 times, or copy this 1 more time. And then I'm going to plot this so that I look at the full right here. So here we go. So now let's look at what happens if I have partial melting. So if I have partial melting, then that means that the water doesn't reach the critical point. It goes from here to there. So this guy is minus Q of the water. So if I look at this as the bar diagram, you could see that the bar diagram only gets to right here. And you could see Q of the water is not as large as AD. So in this situation, you're seeing here between these two that delta Q is negative, right? This is negative. On the other hand, if I have full melting, then this guy actually is larger. So if I have full melting, it's going to go all the way out to here. So this is minus Q of the water. So if you look at this guy here, you could see that this guy is going to come all the way out to here. And you could see that minus Q of water this time, that this is larger than AD. So here we get that delta Q is positive, and because it's positive, that means it melts all the water, and then it will start to heat it up. So now what we want to do is that we want to calculate these quantities. Okay, so here we go. So using the data that's been given, I want to go in and I want to look at that. So here I go. So we already know that it's partial melting, but let's numerically calculate to show that. Okay, here we go. So for this example, for our example, let's calculate these two energies. Remember what they are. They're minus Q water at the critical point versus QAD critical. So let's do that. So the first one that I'm going to do is that I want to calculate minus Q of water at critical point. And this is what we have. We know that the water loses energy. That's why we have the minus sign. And then I have the thermal mass, and this is of water, times the change in temperature of the water to the critical point. So if I plug in my numbers, here's what I have. I have, oh man, I think I have, let me make sure I'm in it. I might have numerical error. I have 200 grams of water. Okay, I have 200 grams of water, so here I go. So it's going to be minus, and look what I'm writing. I'm 0.2 kilograms. Then the specific heat of water, 4190 joules per kilogram degree Kelvin, times the temperature change to the critical point, which is 0 minus 25 degrees C. So when I compute this number, I get positive 21.0 kilojoules, and this is the critical point for the water. Okay, so here we go. So this is the critical point right here. So now I've done one. Now let's get to the critical point for the ice now. So then this guy, I'm going to move this down a little bit. So this is QAD critical. So this quantity requires you to melt all the ice. So this will be QAB, that's to warm it up. But remember, I really need to go from B to D. And that means that I melt all of the ice. So then this will be QBD. So remember, this is to what? Warm up ice. And then this guy is to melt all ice. So then I come in here, and then it's got to be what? I need the thermal mass of the ice times the change in temperature of the ice, plus I'm going to latent heat all of the ice. So if I start putting in my numbers, here's what I'm going to see here. So my numbers now read like this. So the thermal mass, I have 100 grams of ice. Then I have the specific heat of ice. Times the temperature change. So this goes, I end up at 0, but then I start off at negative 15 degrees C or Kelvin, doesn't matter. And then I melt all of the ice. And then I have the latent heat of ice. So in this case, I get joules per kilogram. So if I compute that, look at these numbers here. This number turns out to be 3.33 kilojoules, plus the second number is going to be 33.3 kilojoules. Now remember, this guy is QBD, and this guy here is QAB. So that means here that the total is 36.6 kilojoules to get to that critical point of this guy here. So if you look at this thing, you could immediately see that QAD is larger than minus Q of water. So if I come in here, this tells me here is that I can compute the difference with what I call delta Q. So let me raise this up. So if I put these numbers together, look what I get. I get that delta Q is then going to be minus Q water at the critical point, minus QAD at the critical point, and this quantity then is plus 21 minus 36.6, which gives me negative 17.6 kilojoules. So this delta Q is negative. Remember, negative means, so mathematically, we've shown that delta Q is negative. Which implies partial melting. This means we have an ice water mixture at a temperature of 0 degrees C. So we know what the final temperature is. So then the question, how much ice has been melted? And here's where the bar diagrams become really, really important. So remember, we don't know how much that is. We have to calculate that. Okay? Okay, we have to calculate that. So let's be careful here. So note that, so let's draw a picture. Let's put in our picture here. Okay, so here's our picture from before, and then I'll have to modify it a little bit. Okay, so here's our picture right here. So what I want you to look at this picture here, I'm going to erase a couple of things. So no, we don't get to the critical point. So this never happened. So first of all, look at this question here. So the first thing is that note QAD is not equal to QAC. We didn't get all the way to D. So they're not the same. Actually, I should even make this a little bit stronger. Note that QAD is really for what? This is for full melting. This is not the same as QAC, which is for partial melting. They are not the same. So I got to take QAD out of my picture here. Now I'm going to take this guy out of here. So now what I'm seeing here is that I now have the heat of the water. So we know that we now have partial melting, right? So this now is minus Q of the water. And we know that it only comes this far, right? This is Q of the water. So when you're looking at this, note that we've already calculated these numbers. And so what you're finding here is that we do not know the value of QAC. No, not QAC, excuse me. No. It's got to be between B and C. We don't know the value of BC because it's that green that tells us about partial melting. So we don't know the value of a QBC, which tells us how much was melted. So now use the bar diagrams. So now what we're going to do here is that we're going to use the bar diagrams to compute QBC. So now let's go look at that. Look at our values up here, right? Look at our values up here. We have 3.33, and this 33.3 is what that was for full melting, but it has to be partial melting. So now what we're seeing here is that it looks like this. So if I use my bar diagrams, I have a bar that goes like this. Now note that this is QAB, and we know this amount because we have already computed this. This is 3.33 kilojoules. But now we have this other bar. And this is QBC, which we do not know what it is. But we know how much there is for water. We've computed the water. And it turns out it's the critical point of this water here, which is what? Look at the critical point. The critical point of water is 21 joules. So check this out. So now this right here is minus Q of the water, which is equal to 21 kilojoules. So we now know how to calculate what QBC here. So now that we want to do this is that we want to now mathematically calculate QBC. So if I do that, look what happens here. You can clearly see that minus Q of water has to equal QAB plus QBC. So that then tells me that QBC is then going to be equal to minus the Q of water minus the QAB, but we already have these numbers, so you're getting 21.0 minus 3.33, and that gives me 17.6 kilojoules for QBC. So now I know the value of QBC. In other words, QBC was the amount of energy that melted water, or ice, excuse me. So when I write this out, that means that QBC is this guy's equal to the mass of the melted ice times the latent heat of fusion, which then tells me that I could now solve for the mass of the melted ice, which will then be QBC. With QBC, it's going to be 17.6 times 10 to the 3 joules. Then the latent heat of fusion is 333 times 10 to the 3 joules per kilogram, which then gives me a value of 0.0529 kilograms. So this is the mass of the melted ice. So the leftover ice, in other words, the unmelted ice, is then going to be this here. So we know that the mass of the unmelted will be the total mass of the ice minus the ice of the melted. So we know we had 100 grams. This guy's going to be 52.9 grams. So I end up with 47.1 grams. And this is the mass of the unmelted ice.